In today's video, we are going to look at something called logarithmic functions. Now, where these come from, we kind of put together our previous 3 lessons. We talked about how to find the inverse of a function, which is pretty much when you do the composition of a function and its inverse, everything cancels out and you're left with the value x. And so our process algebraically was you switch your x and your y and you solve for your y. But if we start with an exponential function or exponential equation, that means we would be in this format. So y equals b raised to the x. And so when we find the inverse, again, switch your x and your y, solve for your y. But here's the problem. How do we solve for an exponent? If we don't have nice values that we already know, we have a value plugged in for x and we have a base that works well with raising it to a number, we'd be golden. But we can't do this if the numbers don't work out perfectly. So here enters in the logarithmic function. And a logarithmic function is pretty much just a way for us to express what's the inverse of an exponential function. And the way we write these, if we have a function that's in exponential form, so let's use our function x equals b raised to the y, that inverse function that we created, to do our logarithmic form. Our y, our exponent, is equal to the log or logarithm base b, which again, notice is the same base that we were raising to the y, of x, the expression that was already sitting by itself in the expression. So the way I like to think of it is for logarithms, this is really b raised to the y, and then the x, what it equaled before. And if we kind of go all the way back, if we think about how we even arrived at this, our original equation, y equals b raised to the x, and we took the inverse of it, and then we changed it over to logarithm form. So that means this log, technically, the inverse would be what we started with all the way at the beginning. So that would be y equals b raised to the x. So if we ever, inverse of log. So if we ever come across a problem where we're given, here's a function in logarithm form, find the inverse, all we really need to do, you'll notice, is I pretty much just took out the log expression and still had b, or base, raised to our x that we originally had in our exponent. So let's look at a few ways that we can play around with the format, as well as looking at some graphs and equations, and let's jump in. Alrighty. So one big thing to mention as you're looking at these problems, again, I know some people are using a TI calculator and some people are using a Desmos calculator. Logarithms are much easier to deal with if you're on a Desmos calculator. Now, if you need to do something that's log that's base other than 10, that's where we run into problems on the TI calculator. Again, if you're using that and you're going to be going on to higher math courses such as Algebra 3, Trig, Pre-Calc, and beyond, then you'll talk about how you can actually plug those values into a TI calculator. But if we have Desmos available, all you need to do is make sure that whatever you're typing in looks exactly the same format as what you have on your paper. And so we'll check that out in a future problem on these set of notes. So first off, first set of examples is we're going to rewrite each expression in logarithmic form. So again, I always keep in mind base goes at that little subscript for the log. The exponent that we're given goes on comes from the other side of the equation. So let me go ahead and change my colors. So 2 raised to the 3 equals 8. We know this is a correct statement. 2 cubed equals 8. To write this in logarithm form, we would do log base 2, exponent goes on the other side, so 3 equals 8. It's really just rearranging our expressions to put it into logarithmic form. So this still means that 2 raised to the 3rd power equals 8. Okay, number 2, 5 raised to the 2 equals 25. Again, a correct statement. So if we move our base, which is our 5, into the base position with log, exponent goes by itself, and then 25 goes with the log expression. So log base 5 of 25 equals 2. Just another way to say 5 raised to the 2 power, or 5 squared, equals 25. Now, number 3 looks a little bit weird with the fractions, but we can still follow the same format. Our base is 1/3. So base is 1/3. Exponent was 2. And the expression, which occasionally we'll put it in parentheses, not a bad idea to do with a fraction, just to make everything very clear as to where things are. So log base 1/3 of 1/9 equals 2. AKA 1/3, if we square it, we get 2. It's like writing 1/2 versus 2/4 is just another format. Alrighty, so let's go the other direction. If we're given a log expression, how do we change it over into exponential form? And again, as I'm going through all of these, I'm using these formats over in the logarithmic format. So these are the relationships that I'm using. I'm just going back and forth between those two forms. Alrighty, second set of examples. Write the following in exponential form. Let me shrink this down a bit so we can see our rule up at the top as well. Okay, log base 4 of 16 equals 2. And again, as we're looking at this first set of examples, think about what values would make a true statement on here. Well, 16, how can I get that from a 4? Well, that's 4 squared equals 16. There's my exponential format, and it makes a correct statement. So if this logarithm was written correctly, you should always have a correct statement if you've got all the numbers filled in. Log base 3 of 27 equals 3. Well, 3 cubed equals 27. 3 raised to the third power, we know that's 27. We can even check it on the calculator. And so number 6, wait a second, it doesn't have log written in there. Well, again, your assumed base, if you don't have anything written in, is always going to be 10. And that would have been something too that we could figure out with this. What's our base that we would have to raise to the second power to make 100? Well, 10 squared equals 100. So if you don't have any base written, your base for log is assumed to be 10, and that's what your TI calculator does. Now, there's something fancy that we would need to do to actually change the base. It's technically called the change of base format, but that's not something we're going to be checking out this unit, actually this year. However, if you would like to know how to do that, I am more than happy to show you how to do that through our Zoom chat after you finish watching the video. Alrighty, so now let's start applying this to some equations. So this is where logarithms and changing format between logarithms and exponential equations can really help us out. So next set, and I'm going to go ahead and zoom back in. So we're going to find the inverse of each function. So actually, this isn't solving equations yet. We're going to get to that in a second. But again, I'm going to scroll back up. So again, we have this relationship here. Our logarithmic form, y equals log base b of x. If we go all the way back to how we actually got there in the first place, our original expression, y equals b raised to the x, that was our original problem that we found the inverse of to do this conversion in the first place. So if we have a log function to do the inverse, all we're really doing is getting rid of the log expression. If we're taking the inverse of an exponential function, we're really just throwing log in front of that base and shifting everything down. So in example 7 through 9, find the inverse of each function. So f of x, well, inverse of f of x, throw a log in front of it, log base 3 of x. There's our inverse. That's it. Okay. Number 8, though, is a little more complicated. We can't take where we have that 1/2, which is the base, and we have a 1 that's just sitting there. So I need to do a little bit more work on this one. So first thing I'm going to do is same thing we did last or 2 lessons ago with inverses. I'm going to rewrite my function. So anywhere that I have y or that g of x, I'm actually going to turn that into an x. And then anywhere see an x, I'm going to turn that into a y. So to get the y by itself, first thing I'm going to do is let's move the 1. So x minus 1 equals 1/2, which is our base, raised to the y. So let's go ahead and change this over to logarithmic format. So 1/2 is our base. So 1/2 is our base. Our exponent goes by itself on the other side of the equals. And then we have the x minus 1 which was left. Wait a second, now we have our y by itself, so that means our inverse function, so g inverse of x, is really log base 1/2 of x minus 1. And again, I'm keeping the x minus 1 in parentheses because that expression, I want to keep that together to show the whole thing is getting plugged into that log function, not just the x. Alrighty, so pretty straightforward with number 7. But if we have extra terms, we need to play around with our formats a little bit. So we're going to have to do the same thing on number 9. So again, let's rewrite it. So anywhere we have our y, aka our h of x, that becomes x. And where we have our x becomes our y. And I could put this in parentheses like I have in the problem, or because it's just a single term, then that's fine. Actually, let's go ahead and do that because that shows specifically that that +3, it's not inside the logarithm. It's not inside the function. So same thing as we did before. Let's try to isolate our y, which means moving everything away from it. Let's subtract 3 from both sides. So x minus 3 equals log base 4 of y. And now let's change our format. So he's in logarithmic format. So now let's change back to exponential. So that means for our base, our exponent is on the other side of the equal. So that's x minus 3 is in our exponent. And that equals our y. Y is by itself. So that's our inverse function. So h inverse of x is 4 raised to the x minus 3. So in both of these cases, what I ended up doing is when it was in a format I couldn't deal with, I just changed the format, change it from logarithm to exponential form. Alrighty, so one of the things that you're going to notice today, I'm actually going to give you 2 practices to do because I want to make sure that you're getting enough practice on these pieces. So one of your practices is going to be dealing with rewriting expressions and solving equations, and the other practice is going to be dealing with graphs. Let's take a quick break from our equations and let's take a look at some of our graph problems because this is going to help us understand kind of our domain and range and some of the characteristics of our function that we're going to need to take into account when we solve equations. So if you need to, take a quick break, pause the video, and come back ready for graphs. Alrighty, here we go. So we looked very briefly at logarithms the very beginning of the year. So let's review what these functions even look like. So I have 2 examples here, log base 2 of x and log base 3 of x. And so the difference between the graphs, we actually can find it by looking at our key points. So every time you have a logarithm graph, if you don't have any other modifications, you're not moving up, down, left, right, or flipping it, you're always going to have a point at 1, 0. Okay, then your next point is going to be dictated by what kind of base you have. So log base 2, it has a point at 2, 1. So the 2 points you have on there, you have the point 1, 0, and you have the point 2, 1. And so if we think about this, again, logarithms are our inverse of our exponential function. So your base raised to the 1 power, we need to graph that point. 2 raised to the 1 power is just 2. And so if we think about our log base 3 function, our 2 points that we have on there, we have, again, the 1, 0, because anything raised to the 0 power is 1. And then we have the point 3, 1. 3 raised to the 1 power is 3. And so we can use that to predict what these functions are going to look like. Before we do that, let's talk real quick about transformations. All the same rules that we had before apply. So if I have my function 1/2 log base 2 of x plus 1, well, the 1/2 I know is going to do a vertical dilation of 1/2. And in other words, that's going to shrink it. So it's going to look a little bit shorter than if you were to compare it to your plain parent graph log base 2 of x, that first one. We also have a plus 1 on the end. So that means the entire graph moves up 1. So any points that you know about, you would just shift them up 1 unit. Okay, number 11, g of x equals negative log base 3 of x plus 4. So base is 3, so I'm comparing this to my second graph. What does the negative out in the front always do to any graph? It always flips it upside down. So we're going to have a vertical reflection, technically over the line or over the x-axis. And then we have a plus 4 on the inside of the function, inside the parentheses. Anytime we're inside the function, that always means we're moving left or right. And we go opposite. So plus 4 means we move left 4. So let's look at some graph characteristics, and we're going to start with just our basic function, log base 2 of x. So here we go. So log base 2 of x, if we graph this out on Desmos, and that's how I got most of my pictures, graphing out on Desmos or a program called GeoGebra that you can also use. Here were our 2 points. And the kicker with this graph is it's going to get really, 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 really close to the y-axis, but it's never quite going to touch it. And then the other piece, he's going to go over there. And actually, let's go ahead and switch over to Desmos really quick. So there we go. Let's go over to, there we go. And let's actually graph this out. So I'm going to type in y equals, and then under our functions, we need to go under miscellaneous. That's where our log is going to be. And you see it down towards the bottom, log. And you could actually type this in with, if you have a full keyboard, you could just type in log for log. Now I need to say that its base is actually going to be 2. So we need to do a subscript. So to get to your subscript, hit the little ABC button, and then down towards the bottom, you'll see A with a subscript of B. That will kind of shift your key down, and then we're going to type in 2 for our base, my arrow over, and make sure I have X in that spot. And so hiding my keyboard, I can now kind of scroll up and down on my graph. And as I keep scrolling down, you'll notice that red line, it's hugging the y-axis on there. So it's never actually crossing it. Although if I kind of trace over and try to find a point, wait a second, there's no real point on there. I can't find the point. Let's try there. And so as I go, so hey, it stops right around here because, again, the numbers are getting so small that the rounding on the program can't handle it. But all of the values that we can see, again, you'll notice they're never actually getting down to 0. They're just getting really, really, really close. And so that means we actually have a vertical asymptote at that spot. It also means that we can't cross that point. So our domain is going to be all x's greater than 0. That means, too, I can't plug any negative numbers into my log function. So when we solve equations in a second, keep that in mind. Range, well, the top part of our graph keeps going up. So our range is such that f of x is in all reals. Okay, x-intercept, we have that hitting at the point 1, 0. But we don't have a y-intercept because it never hits the x-axis. So that's a none. Horizontal asymptote, again, none. Vertical asymptote at x equals 0. Increasing, kind of like when we had exponential functions, we're going to be either all increasing or all decreasing. The whole graph, if I start walking on the left, I'm always going to be increasing, and I can't start any further left than 0. So we're increasing from 0 to infinity, and we have no decreasing sections at all. Now our end behavior, again, has a slight tweak. So as x approaches infinity, so in other words, as we're going to the right on the graph, then our y values, our f of x values, are going to keep getting bigger and bigger. So we approach infinity. But as we go in the other direction, here's the kicker. So as I walk on the left of the graph, I'm never going to pass that line, x equals 0. So I actually have to change this up. So as x approaches 0, because it's not going to get all the way to negative infinity, then f of x approaches negative infinity because the part of my graph keeps going down, down, down. Alrighty, so big comparison with exponential functions. With exponential functions, we had the same kind of thing. A lot of times we'd have one intercept, but not the other. We'd always have either increasing or decreasing, but not both. With our end behavior, again, we have that tweak, we have something approaching a different value. With exponential functions, it was always as x approached negative infinity, f of x approached our asymptote. Well, we don't have an asymptote in the horizontal, we have an asymptote in the vertical, so that tweaks how we have to account for our end behavior. Okay, let's look at another graph. So log base 3 of x plus 1. Well, our log base 3 graph before had a point at 1, 0 and 3, 0. So if we have a plus 1 inside the function, what does that mean is going to happen with all of the points on our graph? Well, everything just gets shifted over to the left by 1 unit. So that means we'll come in here, we do cross the x or the y-axis, but just like before, we're going to have to hug that next vertical line. So domain on this one, x is such that x is going to be greater than -1, because everything got moved over left 1. Range is still all reals, goes all the way down, all the way up. So f of x is such that f of x is in the set of all reals. Okay, x-intercept, again, got moved over. So that's actually at 0, 0. And because it's hitting at 0, 0, it is also a y-intercept. So if we move these graphs around, they may have a y-intercept as well. Okay, horizontal asymptote, again, logarithm graphs are not going to have one of those. But they do have a vertical asymptote, which is that x equals -1 to match up with our domain. Increasing over the entire graph, but where does the domain start? -1. And if it's increasing, that means it can't be decreasing. And then end behavior as x approaches infinity. So as you're walking to the right on the graph, your y values keep getting bigger and bigger and bigger. But as you walk to the left on the graph, you're actually not going to get to negative infinity. You're going to get to -1. And your y values will keep getting smaller and smaller to go towards negative infinity. Alrighty, next graph. So number 14. So f of x equals log base 5 of x plus 2. So again, let's figure out our starting points, and you could absolutely plug this into Desmos just to double check. But just like before, when we had a base 3, we had a point at 3, 1. So if we have a base 5, we have a point at 5, 1. So our 2 points to work with are 1, 0 and 5, 1. And then what does the plus 2 do to everything? Everything gets popped up 2 points. So nothing's going to change with our asymptote on this one. It's just we get pushed a little bit over. And I'm noticing as I'm sketching this out, I'm not going to hit a nice place for my x-intercept. So let's pop back over to Desmos just to double check where that's going to be. Alrighty, and so I'm just going to go ahead and change my base. So again, we were at base 5. And then we were looking at plus 2 on the end, plus 2. Alrighty. And so nice thing about Desmos, again, as soon as I click on that graph, my x-intercepts and my y-intercepts will pop up for me. And so clicking on that, I'm at 0.04, very, very small value. Alrighty, so let's write that in. So that guy is hitting at 0.040. So domain, again, doesn't go past the x-axis. So x is greater than 0. All y values are fair game. So f of x is in the set of all reals. X-intercept we just found was 0.04, excuse me, point. Y-intercept, again, never hits the x or the y-axis, so there's no y-intercept. There's also no horizontal asymptote. Your vertical asymptote is still at 0, though. Okay, increasing, again, over the whole graph. We haven't had any of these flipped over. So the only time that we would have decreasing, again, is if you had that negative stuck in front of your graph that flips the entire graph upside down. That would make our graph decreasing. We won't see those as often though. So increasing over the entire range, so from 0 to infinity, and no decreasing. So in behavior, again, as x approaches infinity, as we walk towards the right on the graph, all of our y values get bigger and bigger. But what do I need to change for my second part for moving towards the left? Instead of approaching negative infinity, I'm going to approach 0. And my y's get smaller and smaller to go towards negative infinity. Alrighty, the last piece that we need to look at is solving equations. So again, if you need to take a quick break, go ahead, pause the video, and then we'll check out the last two examples. Or last two sets of examples. Alrighty, so here we go. Two ways that we might see these happen. So when we're solving log equations, again, easiest thing is let's change the format into something we're used to dealing with and then go from there. Now, there are a lot more things that we can do with these equations. We are only going to look at the equations this year that when you change formats, you'll then be able to find your patterns, figure out what value can I raise to make this answer. You'll look at these a lot more in depth in your next math course. Alrighty, so example 15, solve the equation for x. So it's in logarithm form. Let's just change it over to exponent form, which means my base is 2, my exponent is 5, and it's equal to the x, the thing I was taking the log of. Well, wait a second. All I have to do is 2 raised to the 5th power. Okay, so if I do that, then I'm going to get 32. That's it. As soon as we change over to exponent form, this goes a lot easier. So 16, again, looks a little funny, but let's approach it the same way. Our base for our log is 3, so that's the same thing in our equation. Our exponent is that number that's on its own other side of the equation. And that whole expression will equal what we're taking the log of, the 8x, or excuse me, the x squared plus 8x. So let's see, I could simplify 3 squared is 9. And now this looks a lot like a quadratic problem. Let's move the 9 and solve it out. So subtract 9 from both sides. Excuse me, 8x minus 9. And then I can factor this out. So this factors to x plus 9 and x minus 1 to make that positive 8x in the middle. And then set each factor equal to 0. So x plus 9 equals 0, which means x equals negative 9. And x minus 1 equals 0, so x equals 1. And so earlier when we looked at the graphs, we never had negative values in our domain. So unless our graph got shifted over, which this one does, plus 8x would move things over to the left, we still should probably double check that negative 9 as our solution. So plugging that in, let's see, and I'm going to use a little extra room over here. I need to make sure that this expression, the x squared plus 8x, is positive. So plugging that in, let's do negative 9 squared plus 8 times negative 9. Well, negative 9 squared is going to give me a positive 81. Positive 8 times negative 9 gives me a negative 72. And hey, I actually end up with a positive 9 on there. So even though we got a negative answer, it does end up checking out on this problem. So we can use both of those as our solutions. So 2 solutions of negative 9 and positive 1. Okay, 17 is a lot more straightforward. Again, your base is x raised to the 2 power. So that equals 25. So how could we solve for x? How do we undo that squared? Well, let's take the square root of both sides. So square root. However, when we're solving and we take a square root, what do we have to take into account? We have positive and negative. Alrighty, so that means we have that x equals either positive root 25, aka positive 5, or negative root 20, or negative of the root 25, so negative 5. And wait a second, same kind of thing. We haven't really dealt with negatives on here. So real quick, again, let's see what happens when I plug a negative in for my denominator. So back over to Desmos. So again, I'm going to go ahead and use the expression that I plugged in, and let's go ahead and modify that. and type in a -5 and the 25. So I'm just trying to plug that into my original expression, see if it works, and we get undefined. We can't use negative numbers as our bases. We ran into the same problem with exponents. You just can't raise a negative exponent to any kind of even power. The problem is you're going to be jumping back and forth between positives and negatives. Notice what happens as soon as I take out that negative. No problems. So I can't have negative numbers in my bases. So keep that in the back of your brain as you're solving some of these equations. So we have to throw out -5. Our only solution is going to be 5. Alrighty, last set of examples. Here we go. So solve for y in each equation given the value for x. So same kind of thing I'm going to do as before is I'm going to go ahead and actually, no, we don't have to change any formats yet. Let's plug in our x values and see what happens. So 18, y equals log base 5, plugging in 3 for our x. So y equals log base 5 of 5. Now let's change it into exponential form and see what happens. So base is that 5, raised to the y equals 5. Well, what power can we raise something to and get the same number out? So y equals 1. Same thing on number 19. So plug in our 100, we'll see what happens. So y equals log base 3 of 100 minus 19. Except that comes out to 81. Very nice number, because now when I change into exponential form, I'm going to get 3 raised to the y equals 81. What exponent do I have to raise 3 to get 81? Well, if you don't know off the top of your head, go ahead and do a factor tree. So 81 is 9 times 9, and then each one of those 9s is 3 times 3. So how many 3s do we have to multiply all together? 4. So y equals 4. As always, let me know if you have any questions, and check out your practices next.